Corinne Merkel from Rochester Institute of Technology.
All right, thanks, Katie. So we have our lightning talks coming up. So we have, I think, 7 presenters in this session. Each one is going to present about 10 to 12 minutes, and then we'll have some time for discussion in between. So our first presenter is Felix Wang, and he's going to be telling us about distributed localization with grid-based representations on digital elevation models. So take it away, Felix.
Great, thanks. So good afternoon, my name is Felix, and yeah, in this lightning talk, I'll be presenting about a near-inspired distributed localization algorithm that we developed in collaboration with several of my colleagues at Sandia National Labs. And so for our work, we're looking at the problem space of robust sensor-aided localization. This can be informally summarized as estimating where you are from what you see, often with respect to a reference map. Toward this end, we developed a distributed localization algorithm that's based on models of grid cells, and our reference map in this case is a digital elevation model, which is basically just an elevation map. It provides elevation data over a given area. As a fairly fundamental computation, sensor-aided localization has many potential applications in the domain of intelligent navigation, such as terrain relative navigation, which is the focus of this work, but also to general problems in robotics, such as simultaneous localization and mapping. In developing our algorithm, we took inspiration from grid cells in the brain. These are a particular type of cell found in the hippocampus, which can take on multiple spatial scales, orientations, and offsets. And examples of measurements of this grid cell activity from rat studies are shown in this figure in the bottom left. Particularly relevant to our work is that these grid-based representations can be used to encode and decode locations. And as an example, the figure in the bottom right, we see an illustration of how locations along a 1D track may be represented using the activity from 12 grid cells organized into 3 grid modules. The offset of a grid cell with respect to its module is called the phase. And for a given location, we can just read down the rows to find which cells from each module is the most active for that location. And this gives us a phase code. So in the following slides, I'll be walking through how we adapt these grid-based representations to our localization algorithm, show some experimental results, as well as consider what a potential neuromorphic implementation would look like. So extending the 1D example from the previous slide into 2D, we simply overlay grid cell activity over locations of our reference map. For example, here we have a reference map around Albuquerque. There's some prior work in constructing models of grid cell activity patterns in 2D, and the work from Solstead et al. Is what we're using here. And in the figures on the right, we see different sample parameterizations of the spatial scales, orientations, and offsets aligned and then overlaid onto the terrain. And so just like the 1D example for a given location, you can just read out the most active grid cells. And then, of course, as a refinement to that, we can group the grid cells into modules that share the same spatial scale and orientation, with the free parameter being the phase offset within the module. So then moving from grid cell activity to grid module phases in this way allows us to represent the same location with much fewer parameters. To get the phase for a given location for a given grid module, the idea is to find the offset that would align the peak into the activity pattern to that location. And so to do this, we perform an affine shear-like transformation of a location so that with respect to the orientation of a given grid module, and as shown in the figures in the bottom right, this orthogonalizes the original Cartesian coordinates with respect to the shared grid module activity pattern. And then we can perform the modular operation in this orthogonalized space with respect to the grid module's spatial scale, this operation here, to find the phase. Okay, so now that we have a way of translating between locations and phases, we're ready to encode a distributed representation of our reference map. Because our input space is elevations, instead of having to learn something like an embedding space, we can deal with similar inputs directly simply by discretizing over elevations. Here, an elevation bin is equivalent to some small contiguous range of elevations, and the corresponding locations on our DEM forms contour lines as seen in the figure in the middle here. We can pass each location on the elevation contour lines through the grid modules to get their corresponding phases, which are shown in the figures on the right. These are used to populate matrices of phase candidates. And this process can be interpreted as finding the set of possible phase codes a grid module could have for a given elevation bin. And we can repeat this process over all elevation bins and grid modules to construct a dictionary of phase candidates. In practice, this dictionary may be stored as a lookup table of binary matrices, or with respect to a potential neuromorphic implementation, a set of adjacency matrices defining synaptic connectivity. So now that we have a distributed reference map, we can perform a distributed correlation for a given trajectory of sensor inputs in order to estimate the phase codes that we had discussed earlier. In our case, our input is a sequence of elevation readings along some trajectory. The goal is to estimate the phase codes over the grid modules. And we also have some information about the relative displacement of these measurements with respect to each other along the trajectory. And then for the elevation readings, what they correspond to are just these phase candidates that we had mentioned in the previous slide. For the relative displacements, however, we note that a linear displacement in the original Cartesian space corresponds to a phase shift in the grid module phase space. And so we apply these phase shifts to align the phase candidates with respect to some reference point along the trajectory. In this case, we can choose like the final measurement. And if we set it up in this way, the summation of all these phase candidates results in the figure in the bottom center here, where a particular phase code candidate receives more votes than others. And then we take this, it's maybe a little hard to see, but we take the phase code with the largest magnitude as our phase estimate. Although it's largely by construction, what's particularly notable about this is if we track the response activity from consistent phase estimates from a given grid module, the locations it's active over on the DEM resembles the grid cell activity as measured from the rat studies. So we have a quantity in our algorithm that behaves similarly to actual grid cells. So in a sense, we're like reverse engineering the neural computation involved here. For a potential neuromorphic implementation, the summation of these phase candidates into a phase estimate resembles a winner-take-all circuit with the individual phase code candidates competing with each other. So now that we have the phase estimates, we can finally decode back into the original Cartesian space. Compared to the previous steps that I just covered, this one's a little bit more straightforward. Here we just take the phase estimates from like multiple grid modules and sum up their corresponding grid activity patterns. We call the resulting summation a coincidence map because that's what gets highlighted in the image where all the peaks in activity kind of coincide from the contributing grid modules. Much like the phase code estimates, we may estimate the location as the point with the largest magnitude. Something to note with the coincidence map is that as more information is contributed from more grid modules, the location estimate becomes more coherent, as shown in the figures below. Although a single grid module is unable to resolve any sort of location, as you add more, maybe just a handful, a small subset from some ensemble may be sufficient. One last thing I should mention here is that the computation may be, much of the computation may be performed independently with respect to the grid modules. So resulting in a fairly embarrassingly parallel workload that should be in theory be suitable for neuromorphic acceleration. So then taking the algorithm we just went through, going from elevation readings to phase code estimates to location estimates, we now present some results on how well the algorithm performed on a simple localization task. For this, we simulated multiple arbitrary trajectories over our DEM and computed the displacement error between the estimate and the ground truth locations. As an initial experiment here on the bottom left, we populated our dictionary of phase code candidates with 1,000 distinct grid modules, each with their own spatial scale and orientation. And we performed a localization using differently sized subsets of these grid modules randomly sampled on a per trial basis. Our results are in line with what we saw qualitatively on the previous slide. And as we see in this figure, the localization area decreases as you increase the number of grid modules. We also performed some experiments looking at the robustness of the algorithm to different sorts of process noise as they may be relevant on a neuromorphic platform. These included bit flips in the phase candidate dictionary, which corresponds to spikes either not being delivered or being delivered erroneously, and phase shifts, which corresponds to the winner-take-all algorithm preferring a neighboring phase estimate. And so for these experiments, we simply sampled 100 grid modules per trial for their contributions into the coincidence map. And then what we find, as you see in these figures in the bottom right, is that the redundancy that we get from using multiple grid modules serves to make the algorithm fairly robust to this kind of noise. Furthermore, the algorithm showed fairly graceful degradation, most notably in the bit flip experiment. It's maybe a little hard to see the units here, but like at the end here, it's like 30% of the bits are flipped. And here it's about 8 radians of a phase shift. And this is between 0 and 2 pi. So that's fairly significant. I'll conclude with a quick summary and some future directions. This talk presented our work in developing a distributed localization algorithm inspired by grid cell models, which we applied to an elevation data set in the context of intelligent navigation. We also showed that the results from some experiments and commented on the algorithm's suitability to a potential neuromorphic implementation. While we've got a lot of promising results thus far, the algorithm is of course still a work in progress, and there's several trade spaces that we're still actively exploring, such as computation versus robustness, computation costs versus robustness. For future work, our current focus is to transform our linear algebra formulation of the algorithm into a spiking implementation, especially with certain quantities such as the phase estimates resembling the grid cell activity from the rat studies. We're interested to see what the other quantities and computations in the algorithm may correspond to. And I think with that, I'm out of time, so I'll be happy to answer any questions. Thanks for your attention.
Okay, thank you very much. We have time for a couple of questions.
Great talk, Felix. I was wondering if you could go back to the bit flip results you had. Yeah, I was just wondering, looking at the left chart.
This one, yeah.
Yeah, it seems like as you're increasing the grid modules that there might be a nice sort of decaying relationship in terms of error. Have you been able to model that or quantify that?
This is a fairly ad hoc experiment, but it's just like demonstrating what we saw earlier in this slide. But it is just, oh. Okay, it is just showing that the more grid module you use, the more robust it tends to be, or the smaller the localization error. Yeah, this was an experiment more for like a proof of concept. We used like 1,000 by 1,000 pixel DEM, really simple values for the really simple values for the trajectory, fairly simple like parameterizations for the grid module parameters as well. So nothing super rigorous yet.
And maybe one more quick one. All right, if not, let's thank the speaker again. Our next presentation, I believe, is virtual.